Welcome back, Eigen people. So, guys, make sure to like, share, comment, subscribe. If you have not done so already, check out the website, eigenbros.com, even though we're having little issues right now because I just got my Gmail back. But
Nice.
it's not fully finished yet with the website updates, but it will be back soon. Check out Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then also, guys, patrons, thank you guys as always. We greatly appreciate you, supporting the channel, keeping strong with us, having fun with us in the Discord. Guys, if you want to also check out the Patreon, check out patreon.com/Eigenbros. I'm thinking check out a lot, huh?
Check it out.
So yeah, that's patreon.com/Eigenbros. Me and Juan will do at least a 30-minute podcast there every week. So make sure you take a look at that. I'm trying to say something other than
Examine
check
it.
out.
Examine it. Observe it.
Yeah, just
visit-
$1 minimum is all we ask, but you guys can get full access.
Visit patreon.com/Eigenbros for more info.
Thank you, Juan.
And your money. Add your money, please.
Yes.
No, today we have I kind of wanted to I presented this topic this week called about the Solvay Conference. S-O-L.
It's pronounced Solvay?
Solvay?
I don't know.
You tell
I don't
me.
even
You're
know
the-
what that
You're
is.
the foreign language guy.
Yeah, but that's like a weird one, man. I don't even know what the origin of that. I know it's in Brussels, which is Belgium, which is French.
Yeah.
But I never seen a French word that looked like that.
Solvay.
Yeah.
I guess S-O-L-V-A-Y?
Yeah.
Or E-Y?
A-Y, I think.
A-Y.
Yeah.
Well, the thing is, Solvay, for those of you that don't know, it's Solvay Conferences on physics.
Mm-hmm.
Not really something that you hear about a lot nowadays.
Yeah, you don't.
No.
I wonder why. I guess APS took that over. Huh?
Yeah. They kind of put themselves at the top here.
Right.
But
The modern incantation.
yeah, the like to kind of give you to folks a synopsis of, for those of you that don't know what the Solvay Conference is, it used to be this pinnacle of scientific conversations, more like colloquiums centered around where like a lot of the burgeoning fields in physics are going.
Mm-hmm. The big problems at the time.
Yeah. I'm here at the PSL page. It's called the University PSL. It's a Université Paris. Kind of give you an introduction. The early Solvay conferences on physics played a significant role in the evolution of physics in the 20th century. They owe their existence to the generous patronage of the Belgian chemist Ernest Solvay, a lover of science, who co-founded the Solvay Chemical Company with his brother in 1863. And yeah, just this, for like, why is this important? Well, historically, some of the, basically the most famous one, most famous conference was in 1920, what is it, 27?
27.
Yeah.
That's the 5th Solvay Conference. That's the one with the big heavy hitters that you've probably seen. The classic picture, it's got like Einstein, Rutherford, Bohr, Curie, Heisenberg, Dirac. I mean, it's got like pretty much all the heavy hitters of the day.
Yeah, it's interesting that you don't really have those kind of conversations anymore, or like maybe conferences like that where it's like heavy hitters of the day go and congregate and talk. And
well, maybe they do. Maybe it's just APS now.
I don't know. I don't think so. I don't think it's like, here's a photo of all the people that are really important in the field today. Do you know what I mean? Like,
yeah, but
have
how
the
are we
smartest
going to
people
know?
in the
Maybe
room.
they are, and we just
Or maybe they
didn't
are, and we're
realize.
just pushed out of it.
Well, it's like you don't really know. I mean, actually, yeah, I don't even know who the smartest people would be of today. I mean, I guess you got classics like Ed Witten or C.N. Yang, maybe. I don't even know if you count him as a physicist. Yeah, Maldacena, Nimar Kani Ahmed.
I mean, go to Caltech's website, or University of, what is it called? Princeton's Institute of Advanced Studies.
Yeah.
I mean, those places are usually high-strung. MIT, high-strung academics who are working on stuff that's like, leading edge. Yeah.
Yeah, but I guess also it's a little bit different these days because it seems a little bit less lone gunslinger, right? We got a lot of collaborative projects, group efforts, and then a lot of the theory stuff is just so heady that it's like, these guys, are they just wasting their time inventing new mathematics? I say that jokingly, because
Yeah.
of course math is never really a waste of time, but
No.
you know, we're in the realm of like string theory where people aren't really even sure if it's something to invest your time in. So it's like, you know, who do you consider the smartest
Right.
guys of gals of today in physics? I don't know.
Yeah, well, I kind of wanted to read the what would I call this? Just a little opening paragraph for some of you folks that kind of need some context here. You know, in the 19th century, we had this big deviation from classical mechanics, which was the blackbody radiation problem, which is or quantizing blackbody theory with Max Planck in early 1900s, where you needed to solve the blackbody catastrophe thing, where essentially the data that was current models at the time could not account for what was being observed in the experimental data for blackbody radiation.
Did this have to do with the spectra?
Yeah, the spectra.
Okay,
yeah,
the
yeah.
hydrogen spectra?
No,
Okay.
it was different.
Yeah, I'm a little bit less familiar with this because I didn't look at it recently. I know there's the ultraviolet catastrophe.
Yeah,
which
that's what it is. Yeah.
Okay,
Yeah.
which I am actually kind of drawing a blank what it is now.
Shout out to Professor Dave.
We know that the classical physics of Newton and pals reigned supreme for a few centuries. So what were the events that finally exposed its limitations? What was the first thing that suggested there was more to the universe than we had previously thought? This seismic shift was initiated in 1901 when Max Planck solved something called the ultraviolet catastrophe. The problem went like this. Certain objects are called blackbodies because they emit electromagnetic radiation of all wavelengths. The sun is an example of such an object, and we can take a look at the distribution of the wavelengths of light that we receive from the sun. Most of it is in the visible spectrum, which is why our eyesight evolved to pick up this kind of light. But we also receive light on either side in the UV portion as well as infrared and beyond. A hot piece of metal will also do this, and this was the way we studied blackbodies at the time, noting that the distribution depends not at all on the material, but only on temperature, with the particular wavelength that is emitted with maximum intensity shifting left as temperature increases. This maximum will move into the visible spectrum at around 4,000 Kelvin and above. This is why very hot objects appear to glow, like a hot oven, light bulb filament, or the sun and other stars, because objects at these temperatures emit a lot of visible light, as opposed to something like the human body, which at around 310 Kelvin emits essentially no visible light, which is why we can't see each other in the dark. The problem with the black body spectrum was that classical electromagnetism could not account for it. Mathematical models attempting to produce these distributions were able to fit the data for the longer wavelengths, but they did not predict that the intensity would dip down to the left for the UV portion of the spectrum, as experimental data illustrated. Instead, the math predicted that the intensity would continue to increase as the wavelength decreased, and become infinitely large as the wavelength approached zero. Of course, we know that this can't be true, otherwise every time you use the oven, you would get blasted with UV radiation. This contradiction was dubbed somewhat dramatically the ultraviolet catastrophe. In science, if a theory does not accurately align with observations of reality, it must be revised. And so, we realized that classical electromagnetism, as powerful as it is, must have some kind of limitations in its ability to describe light and energy. As we said, Max Planck solved this problem, and he did so by introducing a concept called quantization. We know from classical physics that heat is just the transfer of kinetic energy from one place to another. In the case of a piece of solid hot metal, that kinetic energy takes the form of atomic vibrations, or oscillations. These vibrations are what generate the light we see in the blackbody spectrum. Planck proposed that the vibrational energies of these atoms, and by extension, the energies of the electromagnetic waves emitted by these atoms, must be quantized, meaning that rather than being able to take on any value from a continuous series, they can only possess specific discrete values from a set of accepted values. In this way, he developed this expression for blackbody radiation, where energy is equal to n, which can be any integer, times h, a term we call Planck's constant, equal to 6.626 times 10 to the negative 34 joules seconds, times f, the frequency of radiation. The n value is what results in quantization, as it can only be an integer and not any fraction or decimal in between, meaning that the resulting energies will also comprise a set of allowed values, with anything in between being forbidden. This application of quantization and the accompanying Planck's constant were developed in ad hoc manner, meaning that they were simply proposed for practical purposes, but they allowed for the accurate prediction of the true distribution of blackbody radiation at all wavelengths, which meant that this constant was more than a mathematical fluke, but a clue as to the fundamental nature of reality. And the fact that Planck's constant is so incredibly small explains why the notion of quantization of energy had not cropped up before, because it shows that energy is quantized on such an incredibly small scale that the gradations between the allowed values are utterly minuscule, so as to appear non-existent to any measuring apparatus. Energy appears to be continuous to macroscopic beings, such as humans, but on the fundamental level, it is indeed quantized, even though this conclusion was so strange that most scientists of the time, including Planck, couldn't believe that it had actual concrete physical meaning. This was the first time that quantization had solved such a big problem in physics, but it wouldn't be the last.
Okay, so I think that kind of captures
The essence.
the essence of what the hell that, the black body problem
Right.
kind of illustrated.
Yeah, pretty interesting. I still didn't get what spectral radiance was, but
Yeah, I
he'd
was
at least
trying to-
explain the problem of the mismatch between the classical theory versus the quantum theory.
Yeah, because like that graph is kind of interesting. On the y-axis, it's essentially intensity.
Yeah, okay, that makes
Yeah,
sense.
yeah.
Intensity makes more sense. It's
Yeah.
easier to digest because that's just like what? Something per area. It's like you just imagine a
Yeah.
light, how bright something is
Yeah.
over a certain area.
So spectral intensity distribution of Planck's bob, it's a function of wavelength for different temperatures. So you'll see multiple curves, and they'll have different behaviors at different
Right.
temperatures, but it's
And they're all
plotted
these
against intensity.
Gaussian-looking curves, kind of.
Yeah, and what they found was that as you approach the visible spectrum, you get peaks. But the classical theory of E&M couldn't account for this.
Right.
Until Planck came in ham-fisted. His E equals NH bar or NH omega. Frequency.
Yeah.
Yeah.
F for nu sometimes.
Sure. And funny enough, Planck himself, as the video states, found the concept challenging and defied contemporaneous scientific understanding. In 1908, this Royal Swedish Academy of Sciences refused to award him the Nobel Prize in physics on the grounds that his theory was based on, quote-unquote, an unacceptable hypothesis.
Just cuz isn't good enough for the committee.
Hey, it fits the data. Not good enough.
Hey, man, that's real life.
What do you mean?
I'm just like Planck did the right thing to me. If you just matched it up, you got the experimental data, you threw something in there, it works. Sometimes that's how it goes, man. That's real life. You got to just throw some things in there sometimes. Schrodinger just made up the Schrodinger equation just because,
It fit.
it made sense, I think,
It fit the data.
Exactly. So sometimes you got to do that stuff. This is what they don't teach you.
Yeah, and it says here, even though they poo-pooed Max Planck, Einstein's work on the photoelectric effect was published in 1905. So just a couple years before that, more Einstein's own inner workings of the stuff came out.
Right.
So-
Well, Einstein's a king of elegant, conceptions. So definitely well deserved.
No, well, the thing is, with Solvay did was that he accepted Nernst's proposal, and convened the first Solvay Conference in Brussels in 1911. The conference was attended by 18 of the world's leading physicists, most of whom were already or would become Nobel laureates, including Albert Einstein, Henri Poincaré, Paul Langevin, Hendrik Lorentz, Max Planck, Walther Nernst, Maurice de Broglie, Ernest Rutherford, Heike Ons, Kamerling Ons, Onnes, Marcel Bruyne, Jean Perrin, and one woman, Marie Curie. Unlike earlier international physics conventions, the Paris Exposition Universelle of 1900 and the St. Louis World's Fair primarily deliver reports on successful solutions to scientific questions. The Solvay Conference was conceived as an invitation-only symposium, bringing together a limited number of recognized specialists to debate specific theme defined by an international scientific committee, to contribute to solving unusually difficult scientific problems. So, in preparation for the conference, a dozen scientific papers by participants were sent ahead to all invitees. So, the interesting thing about this is that, this was the first opportunity that people had, that Solvay kind of brought together a lot of important minds. I think him being a lover of science, he helped bring a bunch of people that he thought were leading experts.
Yeah.
Which was kind of not really, he was like the Joe Rogan of the time. No, I'm just kidding. No, he was, what's the best way to put it? Like, he was just kind of.
Maybe the Lex Friedman.
Yeah, maybe the Lex Friedman. No, he just brought a bunch of people together to try to solve, try to bring light
to
or
the most
formalize
difficult problems.
Essentially, quantum theory was in its infancy.
Yeah.
And
right.
have them debate it out, have a safe space for people to really just
right. Well, I think they do that stuff nowadays. I mean, I've seen clips of Ravelli like yelling at people about loop quantum gravity and.
Oh, is he?
Yeah, but I don't really know what the context was. I saw it so long ago before I was really that deep into physics. But I think they have some versions of it, maybe.
Well, I want to say this, like, it was interesting because when I was, in reading about this, the Solvay Conference of 1911, some of the most leading minds, like Poincaré, it'd been the first time that they'd ever thought about quantum theory.
Right.
So, like, for instance, like, Poincaré from the 1911 Solvay Conference, Poincaré returned from the conference convinced by the quantum theory of energy, and Louis de Broglie was introduced to quantum theory for the first time, as his personal notes attest, setting the stage for his future groundbreaking contributions in the field. So, like, you know what I mean? It was the first time that you see de Broglie. De Broglie is like, one of the most famous equations that we use all the time.
Right. It's what?
The E equals...
HC over lambda, is that
yeah,
yeah.
How basically anything you can have... Well, what was it?
It's basically that everything has a wave property to it. So everything has a wave function.
Yeah. And the funny thing was that this was so controversial that they almost denied him his PhD. I remember reading about this. Because there's like, wow, how could you say this?
Right.
They were almost going to deny him. I mean, de Broglie was kind of an interesting guy because he was a wealthy guy. And he had he sort of paid for his education privately, and he was like kind of entering physics as a hobby. And he was just like, I wonder what all these people are talking about. And you're just like, this stuff seems interesting.
Right.
But the interesting thing is that, I mean, they have excerpts and stuff about the notes and what people thought about the conference after the fact. But essentially, so after the conference, people were just like, people were motivated to keep developing quantum theory. And you're looking at if you're looking ahead, you're like, how do we get from this to the 1927
the fifth Solvay
the all-star version of the Solvay Conference?
Right.
But essentially the debate surrounding this was kind of pushed off because right after that, the context of the times of the First World War happened in 1914, and the institute had to essentially suspend any activities, and there was a bunch of scientists that had to flee.
Right.
And basically the Solvay people weren't able to continue the conference until 1919.
Mm-hmm.
So there was like a huge gap of time post-war. And in fact, the third conference took place in 1921 after the liberation of Belgium. So in some sense, like the First World War kind of pushed back the progress that could have been done by quantum theory.
Mm-hmm.
But the funny thing is that the third conference centered around the topic that centered around was atoms and electrons, and this was in 1921. And if you remember back to what was the first? Do you remember the first study they did on the electron?
The first ever?
What was it? There was one famous study by some guy named Gold something.
Oh, you mean Rutherford, the gold foil experiment?
Yeah.
Yeah.
That was like the most famous one, right? That I remember the.
It's one of the most famous ones because it's the one I think that actually enlightened people to understanding the atom was composed of a positive nucleus with negative charged particles surrounding it, I believe. Well, let me think. What did they know from that one? So they knew that when they strike it, they would strike the I forget even what charge they struck the atom with.
Yeah, because the whole thing with Rutherford is they built an atomic the Rutherford model of the atom, right?
Yeah.
Where he had the Rutherford atomic model of the nuclear atom or the planetary model of the atom.
Yeah.
He proposed this in 1911. Funny enough, and it
Was
described
that actually the one that discovered the electron, though? I'm not sure of that.
I think. Yeah, I think it
I
does
know they
because
discovered the positively charged nucleus from
right.
that one.
But the funny thing is the model describes the atom as a tiny, dense, positively charged core, like you're saying.
Yeah.
In a nucleus, in which all mass is concentrated around these light negative constituents called electrons.
Okay. But did they find electrons before that in the other previous model, potentially?
Well, the other model that was competing at the time was was a sort of pudding model.
The plum pudding model. Okay.
Yeah.
Where it was like there were electrons embedded into a positive.
Yeah, that was
plum pudding, or they're putting so the electrons were the plums, and then the pudding was the positive nucleus.
Yeah, and this plum pudding model's
which is wrong.
According to the notes here, it's J.J. Thomson's.
Yeah, that makes
plum
sense.
pudding model.
Right.
So it set aside this, like, it kind of looked at, and that's kind of the most modern picture. If you look at pictures in your textbooks, the Rutherford one is the one that teachers show you in textbooks. You know what I mean?
Well, kind of, no, because I think the Rutherford one is even less so because they didn't even know about neutrons back then. So the Rutherford was just straight up a big chunk of positive charge. Nobody even considered a neutron, right? Because the neutrons weren't even detectable at that time, really.
Mm-hmm.
So the most modern one had to be one that's like the that includes the neutrons somehow.
Mm-hmm.
The one that they considered in textbooks is they just call it, I guess, the
atomic model.
The atomic model, or maybe the solar system model or something.
Yeah. Well, they're saying they're giving credit to him. They're giving credit to him.
Okay, I don't know if I would though, because he didn't have the neutron at that time.
Okay. Well, I would say this.
But maybe that's just me.
For those of you that that kind of want a picture, I'll go ahead and put a picture for the video people here.
But of course, the most modern incarnation is the Schrodinger model, right?
Yes.
So that's the one that they don't even show you in school because it's just too advanced.
It's too woke for you. It's gonna break your poor little brain.
Right. They won't even mention that in high school. They're like, they can't handle that yet. The kids are not ready for that. So,
no. Well, the funny thing is, the Thomson model of the atom, it described it as a uniformly distributed substance. It's kind of like this solid core stuff. But, however, the Thomson model, he would send alpha particles in a beam that were scattered by large angles after striking a gold foil, while most passed completely through. So Rutherford was able to say that the gold's atomic mass must be concentrated in a tiny little nucleus.
Mm-hmm.
So at the time, this whole conversation about, sort of centered around atoms and electrons trying to figure out what the hell is going on. Like,
Mm-hmm. What did he shoot it with? Aluminum particles?
alpha particles.
Oh, alpha particles.
I don't know where
I
the
wonder how they
source
got
was.
alpha particles back then, though. You know,
I don't know.
because that's like a form of radiation that they weren't. I didn't think they were even privy to. What year was it?
1911.
Because remember Marie Curie was doing the radiation stuff, and I thought she was on that trail of even knowing what radiation was, because they didn't even know what radiation was.
Yeah, they were like, "Oh, I'm getting sick."
Oh, but you know what it is? It's probably just because an alpha particle is just helium.
Oh, I see. They were just shooting.
Just helium, I guess. But
Shooting
then, I'm
helium
like, how did they
particles.
harness helium back then? We should really go in depth one day of like how they did these like
How
legit
these
old experiments.
groundbreaking.
Right. Because it sounds so simple in theory, but then you're like, wait a minute, how the hell did they even
How the hell
think
did they
to
get
do
it?
that? Yeah, like how do you shoot helium?
Right.
You know?
Yeah, I mean, like the funny thing was that how incredible that the study was, just
Right.
investigating the atom in these early days.
Mm-hmm.
Rutherford basically, he was trying to analogize to people what this meant or what the atom looked like, and he said it's almost as incredible as if you fired a 15-inch shell at a piece of tissue paper and it came back and hit you.
Wow.
To try to think about the space or the scale of what the atom looked like.
Mm-hmm.
However, the Rutherford
Tissue
model,
paper back then?
it was being rationed for wartime. So the Rutherford model itself was superseded a few years by the Bohr atomic model, which actually incorporated some early quantum theory.
Yeah, the Bohr model, that's the one they show you in textbooks. Because that's when he quantized the energy levels for the electron orbitals, right?
Yeah.
That's the modern one. That's the modern quote-unquote one that they're showing in your high school.
Mm-hmm.
And I guess that's the one that you would consider like the solar system model.
Right. It's sort of like a mix of solar system slash.
I don't even know what solar system. It's just
It's kind of
because
like
it rotates
orbiting,
around.
like,
Yeah.
and it's a bad picture. It's
Yeah. But that's the
physicists-
Bohr model, I think, isn't it?
Right. It's it incorporates that. Because Bohr essentially basically was like looked at the Rutherford model and was like, well, let me quantize the energies.
Right.
And then you had this problem of like, well, the atom, why don't the electrons just dissipate?
Yeah, so you're
Right.
saying why did he want to quantize the energy levels of the
Right. yeah.
electrons? And the
Yeah.
reasoning was because if you have electrons just orbiting around a nucleus, they're going to lose energy, right? Because you can think about it just like how the space station is. The space station orbiting around the Earth, eventually gravity is going to pull it towards the center. The only reason it actually stays up, you got to realize, is because they give it a boost every now and then to keep it in orbit. Or else it's eventually going to decay. Because you can imagine, like, even though space has no
Air.
friction or air,
Yeah,
right?
yeah,
It still is going to have friction to where it's going to start to slowly fall in.
Yeah.
There's no such thing as completely frictionless unless you have a complete vacuum, which is very hard to achieve. If not impossible, I'm not even sure. But yeah, so eventually those electrons should decay into the nucleus, but that doesn't happen. So then the only explanation was Bohr just was like, fuck it. It's quantized. So it just doesn't fall because it doesn't fall.
Yeah. Well, let me just kind of add and continue on here for the building up to the famous Solvay. The third Solvay conference, like I was saying, it was dedicated to atoms and electrons. So you can kind of get this sense of like where quantum theory was. You have the Rutherford model that's kind of already superseded the Thomson model. So you're kind of getting more resolution on what the hell's going on, but you get these quantizations. How do you fit that? Bohr comes in this. So in April 1921, there was some politics going on with the World War stuff, and there was a boycott of German intellectuals at this conference. They were trying to cancel Germans. I'm just kidding. No, but it was
a little problematic.
well, let me just say that the boycott of German intellectuals followed the publication of what was called at the time the Manifesto of '93 or whatever, resulted in the exclusion of some of the conference's most brilliant invited people. Einstein being one of these people. He was a Jewish German man, outspoken pacifist, all this stuff. He did not attend the conference, but he did follow up in the proceedings, like just kind of written responding to what was being discussed at the conferences. Niels Bohr was also absent, but he was sick or something. But he covered the main points in his 1913 paper when he was talking about his Bohr model.
Right.
Albert Michelson was there. Robert Millikan was there in the third one. And it marked a divide. What some people would say that it marked. Basically, it gave a clear picture of quantum mechanics. Because before that, we're all like.
It gave them direction.
Yeah.
I guess because you're saying from the first conference, the whole Blackbody problem.
Basically quantizing.
Right, quantizing for the first time.
Yeah.
And then, quantizing energy for the first time. And then, this new problem of, figuring out what the hell is going on with the atom. And then Bohr eventually quantizing the energy levels of the electron. They're starting to see this pattern of quantization occurring.
But even then, I think the Bohr model fails, right?
In what sense?
The limitations of the Bohr model in that.
Well, I think the Bohr model failed more as we delve into quantum, right? Because it didn't account for some of the parts, like the Schrodinger model is the most advanced one, right? Because that has to do with all the probability, what do you call them? The probability solutions, I guess, for like the hydrogen atom. You can see that all these energy levels have these specific probability distributions, which are not nearly, it's not nearly as detailed in the Bohr model. It doesn't show all that.
Yeah.
It doesn't show those excited states and those different transitions of probability that it has. Yeah. And there's no mention of even a wave function in the Bohr model, right?
No.
It's very, very simplified. It's
very simple.
Yeah, it's just saying energy levels, quantum, the electron energy shells, they're quantized. That's it.
Yeah.
Just to get around the problem.
But that's like a very helium model, or what is the basic?
Oh, like heliocentric, you're saying?
No, the basic helium model where it's like one proton, one electron. And
hydrogen. Well, not even, because the hydrogen one is complicated, right?
It's a lot more complicated.
The hydrogen one, that's only one proton and one electron, right? And that's the one that is like that you see the pictures of all these crazy like 3D models of these dumbbells and whatnot. Showing those wave function, those wave function distributions for the electrons. So it's like. Yeah, even that. It's just like it's even simpler than that. Right?
Yeah,
it's just a very simplified model.
Well, I do want to talk about the fourth conference. So the fourth conference took place in 1924. I think. So for context, historically at the time, we just got a World War I ended. I think it lasted for 5 years, 6 years.
Don't look at me. I mean, I played a lot of Call of Duty, but I don't remember dates.
But there's still a lot of stress around like German intellectuals and stuff. And in 1924, there was still this this kind of side-eyeing, this kind of sort of barring of German scientists being part of any. Basically, don't leave them alone in the room.
Right.
They might plan some really heinous stuff. But anyway, the fourth Solvay Conference on Physics was devoted to electrical conductivity on metals and related problems. And this was in 1924, 2 years after Solvay's death. But this time there was 13, there's participants from 13 countries. But Germany was still not allowed to go.
Damn. Germany, get your shit together, guys.
Well, Einstein famously refused to attend. Like, he was just like, I'm not going to go if you keep basically canceling my fellow Germans.
Right.
He's like, I'm not going to go if my German colleagues are barred from going. It's not right for me to take part in the Solvay Conference because of my German colleagues being excluded. He said,
Slighted.
This is quoting him. In my opinion, it's not right to bring politics into scientific matters,
Mm-hmm.
nor should individuals be held responsible for the government of the country to which they happen to belong.
Yeah, do you agree with Einstein on that?
Oh man, it's kind of he went out on a limb here. Really, that must have been a real controversial take.
Yeah, yeah.
You know,
I think Einstein's heart's in the good place, but like when you are potentially creating atom bombs and new weapons, the smartest guys are going to be leading the charge potentially, right? The
Yeah.
Manhattan Project is a real thing.
right. And I think this is the reason why the Solvay Conference is interesting and the proceedings. It's just because the intersection of politics and science at the time was probably greater than any other time in the world, right?
Mm-hmm.
Because I mean, you're talking about, like you're saying, a development of basically very advanced weaponry that only comes through the knowledge of science. And I think maybe I wouldn't say he's wrong. I think ultimately he's correct in his like principled response, but I think in the context of the time, it would make sense to be like, we can't take anyone for good measure. We can't really allow it. The optics of it are bad. Like if we allow Germans to come and talk, I don't know. How do you feel about it?
Yeah, I think it's like that's the shitty thing about war. It's like even though they're not your enemies, like Einstein, I'm sure no one was an enemy of Einstein in that circle. Well, I won't say no one, but I'm sure he's a respected guy.
Yeah.
Scientists are kind of in this weird spot where politics kind of shows up on our doorstep.
Right. Yeah.
But it's like you gotta at the end of the day realize that you are a part of a nation's war, and then you do get stuck in these awkward situations where you have to now choose a side.
Yeah.
It's like being in prison.
Yeah.
It's like you may be a guy who grew up in a particular place. Let's say you were a black dude who grew up in the suburbs, but in prison you're gonna have to go with the black team or whatnot.
Yeah.
It's like it forces your hand just because that's just what it is.
Yeah, and the tribal stuff. It's
The tribalism.
Yeah, and I mean, like, and the funny thing, and this is kind of what led to the most famous Solvay conference, because it wasn't until Germany officially joined the League of Nations, which I think preceded the United Nations. It wasn't until basically Germany was like, all right, we'll calm down and set aside our racial prejudices and stuff, that they were allowed again to participate in European or sort of intellectual circles and conversations. And that's when the big dogs came out. So fast forward to 1927, because from 24 to 27.
This is MJ era.
Right. So just to give you some context too. I mean, World War II happened. It happened during. Whoa, what the hell? Sorry, I'm trying to look up the dates here. I'm not a history buff,
No.
so I can't really say. But World War One, not World War II. What the fuck?
Yeah, World War II is 40s.
40s, yeah. So World War One was 1914 to 1918, but there was still a lot of animosity.
Yeah. Towards Germans and whatnot.
Yeah. And I guess rightfully
But they were
so.
beaten down, I guess, at this point. So they were like, you guys can come back.
Yeah, and in the 1920s, I think Hitler especially, I think he was in jail at the time.
Oh, was he?
He was writing his little books and stuff.
He was building his hatred.
It's like, they put me in jail. No, but the fifth Solvay Conference in Physics held in 1927 is the most important conference prior to World War II. The German scientists were again allowed and welcome, and Einstein had been appointed he'd been appointed sort of the head of the International Scientific Committee. So the committee was the scene of fierce controversy between prominent physicists, including Bohr and Einstein, on questions of quantum mechanics, and specifically the Copenhagen interpretation. And it's still talked about to this day, because that's kind of where they hammered out how you should interpret quantum mechanics.
Right.
Yeah.
It's kind of the safe way. if you will.
What do you mean?
Because Copenhagen doesn't really try to make too many assumptions, right?
Mm-hmm.
They try to really stick with, what the math is saying and trying not to assert too much language onto it.
Interpretation. And all that?
Right. It's kind of like the safe way to talk about quantum without getting too much into like quantum ideology, if you want to say.
Yeah.
Like, because then for instance, the many worlds might be like saying, it kind of makes a stronger statement that there is another timeline or something that exists, which is like, how can you say that really?
Right.
Just as an example.
Yeah, so, excuse me. The topic in 1927, which was the most famous one, was electrons and photons. And this was probably the most heady one, right? Because now you're talking about, the quantization of things that have mass and things that don't have mass. Like, how do you treat these two things that are quantized particles? They're trying to make sense of it, and like, I don't know, just you had some incredible conversations here, and I wanted to go down the list of the people that are here.
Oh, right. I think you got the same list I got.
And the no, I don't actually. Do you have your list pulled up?
Yeah, you want me to pull it up?
Yeah. The 1927, the most famous Solvay.
Yeah, so I'll just read off the names. I mean, there's some I didn't recognize on there, but I mean, it's crazy the number of people on this list. You're like, damn, this is like everybody in every textbook I've ever read. Yeah, so here we go. It says 17 of the 29 attendees were or became Nobel Prize winners. So
that's like 50% of.
It's
like
over 50%.
When you go into a lecture hall and it's the opposite of what your professors tell you.
What do you mean?
Look at you, look at both ways,
Right, like the people around you will be gone.
Yeah.
Right. This is the exact opposite.
These people will be gone. It's like, look around you. These people here in the Solvay Conference, you're going to be somebody's.
Or these people will be your superiors.
Right.
All right, so it says we got Auguste Piccard. I don't think he's related to
from Star Trek.
I don't think this is the TNG. I believe that was what was Picard's first name?
Alfred?
No, he's French. Jean-Luc.
Jean-Luc.
Yeah. And then we have Émile Henriot. Then we have Paul Ehrenfest, who is a name that's familiar.
Yep.
Eduard Hertzen, not familiar with him. Then we had Théophile de Donder, not familiar. Erwin Schrödinger, of course.
Classic.
Jules Emile Verschaffelt. Wolfgang Pauli.
That's branding, really, what it comes down to. Some of these guys with difficult names.
They need better names, you think?
Yeah. They need better scientific names.
Yeah, like Jimmy Neutron. I mean, that guy's born to be a scientist.
Yeah.
We got Wolfgang Pauli, Werner Heisenberg, Sir Ralph Howard Fowler.
Nice.
Leon Nicholas Brion.
Nice.
So that's Brion zones.
Nice.
Peter Debye energies. Martin Knudsen. William Lawrence Bragg diffraction. Henrik Kramers.
Kramer's
I think he said the N-word. They banned him.
Yeah, they banned him from the conference.
Yeah.
No, Kramer's rule.
Kramer's rule. You know one. What is that one?
Yeah, Kramer's rule. You're not allowed to go into comedy shows with any preconceived, maybe prejudices. No, Kramer's rule is it's something that's in quantum mechanics that we use.
Yeah, sounds kind of familiar.
Is it CR or it's CR, right?
Can't remember. This guy's KR.
Oh, this guy's K?
Yeah.
Oh, okay.
I can read his profile. So it says Kramers was the first foreign scholar to seek out Niels Bohr. He became his assistant and helped develop what became known as Bohr's Institute, where he worked on dispersion theory. Oh, so maybe he's related to Debye somehow?
Yeah, Kramer's. Okay, yeah. So I remember Kramer's in quantum mechanics. It's the Kramer's degeneracy theorem. States that for every energy eigenstate of a time reversal symmetric system, there's at least one eigenstate with the same energy. In other words, every energy level is at least doubly degenerate if it has half energy spin. This is H.A. Kramer?
This is, Hendrik.
Yeah.
All right. That's what's up.
Big head guys.
We got Paul Dirac.
Yep.
Arthur Holly Compton. Compton scattering.
scattering.
Of course, I didn't even say anything about Dirac because, I mean, if you don't know Dirac, why the fuck are you here? Louis de Broglie. Classic. Max Born. Born's Rule. We got Irving Langmuir, who I've heard. Langmuir is a familiar name.
Yeah, it is.
Let me see. It says he was an American chemist and physicist. His most noted publication was the famous 1919 article, The Arrangement of Electrons in Atoms and Molecules. I did not read that, but sounds cool. Max Planck, of course. Niels Bohr, of course. Marie Curie. We've got Hendrik Lorentz force, Lorentz transformations, and Albert Einstein. And then we've got Paul Langevin. I know him as well. It says he developed the Langevin dynamics and the Lagrangian equation. He had a love affair with Marie Curie.
Ooh,
So
saucy.
you know why they were at the Solvay Conference.
Yeah. Writing letters.
Doing more than writing letters.
Yeah.
Charles Eugene Guy. Charles Thomas Rees Wilson. Sir Owen Willens Richardson. And that's the last one.
Yeah, I remember Richardson.
It says Richardson won the Nobel Prize in 1928 for his work on thermionic emission, which led to Richardson's law. I'm not familiar with him.
Yeah.
So,
Big, heavy
hitters.
Heavy hitters.
Yeah.
I mean, if you literally open any textbook and as you advance, maybe even in the field of physics, you will hear these names.
Most of them on there.
Most of them.
Yeah.
Even chemistry. I mean, a lot of these were physicists and chemists just because. And the overlap was because at the time, chemistry and physics were kind of
Quantum's prime for that, right?
at the intersection. Yeah.
Quantum stuff and chemistry just go really hand in hand. I mean, what's the quantum version of chemistry in college called? Is that organic chemistry?
No, I think it's called physical chemistry.
Physical chemistry,
Yeah,
okay.
yeah. Quite literal on the take
Yeah,
here.
yeah.
But they essentially in physical chemistry you cover orbitals. You're doing Schrodinger equation stuff. I remember one of my chemistry friends was basically like, "Fuck this." I'm like, they're almost going to quit just because.
Right, I didn't sign up to be a physicist, damn it.
They call it PChem, but they're like physical
That's
chemistry.
it, PChem, yeah.
They're just like, no, I hate this.
Yeah, so if
very
you're any
hard.
kind of scientist at the end of the day, you will always be slightly a physicist. Because
Yeah.
all roads lead to physics, basically.
Yeah, and this man, and the impact that this had. I mean, you still have. They were having debates. Bohr and Einstein in that conference, kind of were at each other's throats, just interpreting. We're still having these debates today.
Yeah.
Like the Copenhagen stuff. How do you interpret quantum mechanics? What is the right way to think about the data that we see?
Right. It's the whole quantum philosophy, if you will.
Bless you.
Thank you.
Yeah, there were for roughly 5 days in 1927. Niels Bohr and Albert Einstein were kind of. There was a lot of famous quotes here too, discussions between.
God does not play dice. It's one of the ones that Einstein did during this time. And then I think Bohr said, "Stop trying to tell God what to do." Or something along those lines. I probably made it sound less cool than it was.
The Bohr-Einstein debate centered around the philosophy of science, essentially discussions with Einstein on the epistemological problems in atomic physics. The debates were centered around Bohr's Copenhagen interpretation, which centered on his belief of complementarity that was valid in explaining nature. And their debates helped solidify quantum mechanics, and but they both would debate ad nauseum, and Einstein took it to the grave, like his I mean the most famous what was it, the EPR paradox. He still kept at it. The man was a madman.
The EPR paradox.
Yeah, where he was like the Einstein
Podolsky-Rosen paradox.
talking about the sort of paradox that one would get with the Copenhagen interpretation.
Can you enlighten me on what it is again?
Yeah, if you have two spatially separated or two time-like separated systems. Basically, a signal cannot be sent fast enough to be.
Oh, that's to do with entanglement?
Yeah, but it's a complementarity thing too. It's like a particle and wave kind of picture of quantum mechanics where you can't, or it's almost like it argues against locality, you know.
Yeah, so it's the one that has to do with saying that objects are local and real, right? But we actually find out that objects are non-local and non-real?
Non-local and well, the argument is that it argues against realism, this idea that, you know, which is arguing against non-locality. Things that are spatially separated can have some kind of correlation.
Well, I thought realism had to do with whether the particle existed. It always had a state or
right.
not,
Exactly. Yeah,
right?
yeah.
But the non-realism has to do with the superposition state.
Right.
The particle,
which is a Copenhagen.
Right, where the particle doesn't necessarily have a state. It's some mixture of states,
Right.
and it only settles on a state once it's been interacted with.
Yeah.
And then, of course, locality has to do with the fact that everything's constrained by this radius, this radius of light, right? Where nothing can propagate faster than the speed of light, so that you don't affect causality. But then that's not the case, because entanglement, you know, shows you that there's some correlation between atoms or molecules or whatever your system is your quantum system, that can actually propagate some kind of change.
Correlated.
There's some correlation between those two that happens regardless of whatever distance they're at.
Right.
So any arbitrary distance, and it's not constrained by any light radius, any radius of light. That's one of these. Those are concepts that are very hard to get your mind around.
Yeah.
Unless you really have thought about it.
Right.
So don't feel too bad if you don't understand what that means. But yeah, the way that I mean, those are extremely valid things for Einstein to bring up. I mean, because the whole absurdity that you get when you can, or at least that Einstein pointed out with a non-real thing, is like. He assumes the moon still exists whether you observe it or not.
Right. Einstein's point was that he argued with Neil. That's a good famous quote.
Yeah.
He's like, you're telling me that if I don't look at the moon doesn't exist until I look at it.
Right.
And Bohr said something like, essentially like, yeah.
Yeah. And the fucked up part about it, even more fucked up part about it, is that's right. Like, that's the reality we live in.
Right.
You know, we're living in a quake, a quake simulation where, it's like only draws what's on the screen.
Well, maybe
no, that's a little bit misleading.
It's a little bit disingenuous, but
because this really has to do with when they say observe, they're trying to make it more romantic, but it really just is anything that's interacting. Like the moon has to have interactions in order for it to have a collapsed wave function.
Right. The matter within. Right. The matter needs to interact with its environment for it to take form.
And of course, the moon is so huge; it's composed of so many particles, so it's going to have interactions regardless, right?
Yeah.
It's like it's highly unlikely that there won't be any interactions.
Yeah, and for those of you, to give context to people that don't know, and maybe you're a listener and like, yeah, what the hell is the Solvay Conference? And the EPR, or Einstein-Podolsky-Rosen paradox, was a paper that was introduced in 1935. As a debate between Bohr and Einstein, centered around him particularly thinking that quantum mechanics was incomplete. But
this is hidden variables.
Right. He was also
right.
And he was saying, can quantum this was the title of the paper, can quantum mechanical description of physical reality be considered complete? And yeah, I mean, it's just this paper still is talked about to this day. We're talking about studying the foundations of quantum mechanics, just based off of the debates that Bohr and Einstein had.
Right, and it's also beautiful, the resolution they came up with, Bell's inequality, demonstrating that reality is this has this underpinning of probabilistic, or this probabilistic nature. I don't know a good way to say it, but yeah, it's like Yeah, Einstein was saying that there's these hidden variables potentially that we just don't understand the full picture of quantum mechanics. You know, these particles are in a definite state, you know, and they are local, but for some reason we just can't see behind the curtain. But that's actually not true, and Bell's inequality shows that through probability, because since quantum mechanics is this probabilistic framework, it's actually crazy that in quantum mechanics probability, we get these different probabilities than if there was hidden variables. So the real picture of quantum mechanics has different probability distributions for how, when you measure a particle, how many times that particle will show up as, let's say, spin up or spin down or whatever it may be that you're measuring, whatever quantum property you're measuring. That probability in the quantum world is different than what it would be if there was some hidden information.
Right.
And you can actually prove that experimentally. And
Insane.
you get this sine wave pattern depending on how you measure that system of spins. It's a classic experiment that they do. I think utilizing Stern-Gerlach maybe, or maybe not. I don't remember what exactly the experiment is with that one.
But it's basically a quantum system.
Yeah, I think they
You
use
should have this
spins
outcome.
or something.
Right, but they show that you should have this outcome if you assume no hidden variables. It should be this like rather sharp sort of data that you get, but you get
if you ever do like synthesizers, it's like a triangular wave pattern. Is the hidden variable hidden variable graph you'll get versus the sine wave that you'll get, which is the real quantum picture.
Yeah, and I kind of want to give more like I know we talk about how important it is and everything after, but I do want to like sit and pause in that time of all these great people coming together. I do want to give a sense of what it was like.
Back then?
Yeah, like seeing these people come to this conference and debate about this. Here we go. I'm going to show you some video, some rare footage of the time. Okay, here we go.
The film opens with quick shots of Erwin Schrödinger and Niels Bohr. Auguste Picard of the University of Brussels follows, and then the camera refocuses on Schrödinger and Bohr. Erwin Schrödinger and Niels Bohr followed by Picard. Schrödinger, who developed wave mechanics, never agreed with Bohr in quantum mechanics, nor with Werner Heisenberg's uncertainty principle. Solvay gave Heisenberg an opportunity to discuss his new theory. Here's French physicist Léon Brillouin, Hendrik Kramers, Bohr's former assistant, and Paul Dirac talking with Max Born, whose statistical interpretation of the wave function ended determinism in the atomic world. These men, Bohr, Heisenberg, Kramers, Dirac, and Born, together with Wolfgang Pauli, represent the founding fathers of quantum mechanics. On the other hand is Louis de Broglie, who wrote his dissertation on the wave nature of matter, which Schrödinger used as the basis for wave mechanics. The owner of the camera, Irving Langmuir, is seen chatting briefly with Bohr. At Solvay, Bohr refined his thoughts on complementarity and sparred with Einstein over the implications. Here he's with Paul Ehrenfest. Kramers' work in Copenhagen on dispersion theory was essential to the development of quantum mechanics. Langmuir, an American chemist at the GE lab in Schenectady, hence the camera, had recently broken his leg and appears to explain to Ehrenfest how he gets around. By 1927, Dirac in the middle had independently developed quantum mechanics and made other significant contributions, as had Wolfgang Pauli, who formulated the exclusion principle. A lively Madame Curie, Born and Pauli working out a problem. Note the changed demeanor as the participants exit from the meeting, except for the smiling William Lawrence Bragg and Peter Debye, Arthur Holly Compton, Owen Richardson, Max Born, Madame Curie, Hendrik Kramers, H.A. Lawrence, Paul Langevin, Albert Einstein, whose famous response to Born and the statistical interpretation of the wave function was, "God does not play dice." Bohr, Planck, Pauli, and Belgian soldiers, a portentous conclusion.
Yeah. This is 5 days of them
Badass.
sitting in a conference hall or sitting in a hall, presumably.
I think it's crazy how we lived during a time. How we were alive when Paul Dirac was still alive.
Yeah, I know.
It's fucking crazy.
Yeah. I mean,
You
I
don't think about that, but like, we literally could have met Paul Dirac.
it's sad that we didn't.
I know.
Okay, so they were talking about Max Born and how he said that his contribution in 1926 when he proposed that quantum mechanics are better understood as a probability without any causality, and that Einstein was kind of like the guy there that was more of like taking the oppositional view of that
Well,
was
they also
being
said
developed.
Schrodinger didn't like it either.
Right, Schrodinger famously didn't, but and he's the one who came up with the
Like the most important quantum equation.
but also the most colloquially known example of the like quantum mechanics.
Oh yeah, the Schrodinger's cat is the classic, right? Yeah, of course. It's what everybody repeats who doesn't even know anything about quantum mechanics.
Right. So the cat is dead and alive.
Right. It's like,
I just want to retire that example almost entirely.
yeah, it's just so
Stern
confusing.
Gerlach is probably a better one.
Yeah, that should be more mainstream, huh?
That should, yeah. But I want to say that in those 5 days, we need to have more of this because in those 5 days you have so many. You have a lot of famous. You just have so much controversy and like debate that is still. I mean, we get the Schrodinger cat example. Both Einstein and Schrodinger rejected the interpretation of a renunciation. They basically said causality is like our primary, our totem, our principle of like realism, and it was rejected at the time.
Well, not realism, I'd say of localism.
Localism.
Yeah.
Yeah.
Because causality has to do with the speed of light, right? And being local means that you're within that radius of light.
Yeah, and even I mean they debated a lot. I mean Heisenberg had this. He would have disputes with Bohr that Heisenberg had a matrix mechanic view. Essentially, like he introduced. He sought that linear algebra was compatible with at explaining a lot of the mechanics that we see. Yeah.
Interesting. So Heisenberg was the guy.
Yeah. Was and he noted that it was not compatible with the Schrodinger equation. And he was just like, "What the fuck?" But they kind of, we kind of live with this. Like, sometimes we use the Schrodinger model, but in most advanced cases, we use the Heisenberg picture more than anything.
Right. But the Schrodinger stuff, we still. I thought it was compatible because it's like Schrodinger stuff.
It's toy model stuff, though, don't you think? The Schrodinger stuff? Like, we deal with particles in a box, which is a good approximation.
But I mean, like, what do you mean that matrix math, like linear algebra, is not compatible with the Schrodinger picture? Because the Dirac notation, the eigenstates, let's say,
But that's
are matrices usually.
Right.
So it is compatible, isn't it?
No, but Dirac notation is. Oh, I see what you're saying.
Yeah.
At the time, I guess they didn't see.
Yeah,
the
I think they probably just didn't see the connection back then.
Right.
Because Dirac notation, I think, is what unified it. Because
Right.
Dirac showed that you can do like these outer products and stuff with these Bra-Ket notation and
Right.
all this stuff, and then they became compatible.
Yeah.
So maybe at one point it wasn't compatible, if that's what you're reading.
Yeah, I don't think they saw the
connection.
Yeah. Well, because I mean, for clarification, the Schrodinger equation is calculus. It's a second order differential equation. It's a
right. And it's not obvious to even invoke matrices a lot of times, right?
No.
Right.
Well, that's what I'm saying. Like, what made it more accessible was matrix mechanics. Was like people doing order operations and row reduction.
Right. And just seeing that you can have multiple, you can get the multiple different probabilities for each eigenstate.
Say that again.
Or let me say, so the probabilities would be associated with the eigenvalues.
Right. So
Right, and then the eigenvalues would be in the matrix, and then each eigenstate might have its own eigenvalue.
yeah. So what's
So it's
more
like a system of equations in some sense.
right? Exactly. And I think what made the Heisenberg picture more accessible to scientists was because, in the lab you typically measure, or you can measure energy. You know what I mean? So your data looks like
Well, you can't measure it directly.
right.
Yeah.
Well, I'm
so
saying
you got to be
like,
careful.
okay, yeah. Let me. But
Yeah,
let me.
'cause
be
what
more,
is energy, right?
Right.
You can measure like a frequency, which is
Right,
related
right,
to
right,
energy.
right. Yeah. But I'm saying it's more clear to just put these values into some kind of data column thing and manipulate your data using linear algebra.
Yeah.
As opposed to Schrodinger's, I think picture is a lot more gives a lot more insight into the physics. I think because it's
Yeah.
right, don't you think? Like
It just depends.
What do
But
you
yeah, I guess you're focusing more on the calculus usually in Schrodinger's picture. But
but no, but
I don't know. It's like because they're both so linked for me. Because we're living in a time where they're just completely all unified in some sense. Like I flip between matrix math and then Dirac notations so seamlessly. Like I don't even think of them as separate. So it's hard for me to like even.
Well, I'm talking about
distinguish
like
in my mind.
E. Yeah, I guess we are. Kind of, I was saying like energy. The energy times the wave function is equal to the Hamiltonian times the wave function. So I don't know.
But with the Hamiltonian's a matrix, right?
It can be, yeah.
Yeah. Well, it's an operator, and then operators are typically matrices, so it's
Yeah.
like, yeah, I unify that
I don't.
picture.
Yeah,
in my
I see.
mind
I see.
typically.
Yeah. I think you.
Unless
see
you
that.
have maybe one eigenstate, but then if you have one eigenstate, that's almost like not even quantum, right? Because it's the matter. It's usually the different number of eigenstates you have an associated probability, and then it becomes quantum.
Yeah. So
I guess not one eigenstate. I'm sorry, one eigenvalue. I'll say. My bad.
Yeah. So I kind of want to center the conversation more about like. I don't think we have many of these anymore.
What? Oh, like a Solvay type.
Yeah.
I can't speak on that because I am not that in
You're like,
tune
I'm not
in
invited.
the. I mean, we never got to reach the level of professor, so we don't really know what they really do. We know they go to APS and whatnot, but then APS is like, that's American Physical Society. That's like the big conference for all physicists. And usually what that is like a lecture, and they just talk about whatever they just discovered or whatever they think is really cool. But I guess you're saying like there's no like real debate style like big prominent scientists like
No, to me
hashing it out.
No, to me the what makes the 1927 conference so important and why it's in our textbooks and everything is because that was the first conference. Well, maybe not the first, but maybe the first time we had all these big minds tackling the foundations.
Mm-hmm.
Really kind of like debating things, and maybe in the construction they were kind of, how would you say, formulating what the prevailing sort of narrative is about this subject, but I don't know if we have that. I don't know if we have those big things anymore. I don't know if like you could invite someone like say Juan Maldacena or Leonard Susskind, these kinds of big dudes that know quantum mechanics. They're maybe studying the intersection between quantum gravity. I mean, studying
now
something.
it's all about quantum field theory and then general relativity.
I don't know if we're having the same debates centered around that as much.
Maybe not. I'm not really familiar.
Let's get the Eigenbros on it. Let's be.
We need to host our own conference.
Yeah, well, we're
Solvay 2022.
Because I mean, I'm a quick Google search of quantum gravity conferences. I'm sure it's going to be laden with a bunch of
Quantum gravity people. Well, maybe that's also the problem is that physics is just too. Everybody resides in their own mountaintops these days because it's just so deep that you can't really do that anymore. Because like imagine like a condensed matter physicist trying to go to a quantum gravity conference. They're gonna be like, "What the fuck are any of you guys talking about?" It's just physics is so what do you call it? Isolated by specialization now. It's just like
Oh, you're saying there was more intersection.
Yeah, because those guys were doing it all back then, kind of in
Yeah.
some sense. Like
Yeah.
nowadays, it's like, who the hell could just talk about cross-disciplinary like that? Like,
Yeah.
imagine trying to like talk about, just imagine a condensed matter. Like, imagine the top condensed matter physicists trying to talk about theories of everything and quantum gravity, Higgs boson stuff.
Yeah.
They're just going to be out of their element. They're going to be like, okay, I guess it's legit.
Yeah. Well, let me just say this. So the most famous one, or if you Google it, the first result you'll get is the International Conference on Quantum Gravity and String Theory, and that lasts 2 days, 10th through 11th, 2022.
So then that would be the modern version.
Yeah, but to me, it's not like. Hopefully, you would see. I would think that you would see people that are really big, but there almost needs to be like you need to. I would love to see like the big minds, the galaxy brains of today. You know what I'm saying? Like we're forcing them to be in a room together.
But would they talk about the same subject, or would they just talk physics in
We
general?
give that's the same thing. We give them like 12 papers or something, and it's like here we're all read on the same thing.
But that's where I'm like, I'm not sure it would work, because Ed Witten, string theorist, may not have the same depth of knowledge as, like, I don't know who's one of the prominent
String theory guys.
like other fields. Like, I guess it works when you're in the field of like string theory / high energy, because that's more in line with theories of everything. But if you're talking like condensed matter or astronomy guys, then they're kind of out of the conversation.
Yeah, but I mean that's kind of how it was then too, right? Don't you think? Like people were out of their.
I guess
mean,
you're right.
You know what I mean?
So then I guess it's really just the high energy / the theoretical high energy people. Then that's kind of where it's at.
But you also need to have an intersection of experimentalists, I think.
Okay, yeah.
You know what I mean? Like you need to have. Imagine having.
But then you're really just talking to like a high energy conference then.
No, I mean there would have to be like some leading people. I would love to have some quantum information people there, like.
Okay, that's getting into a different conversation then.
Yeah, because I think you need to talk about the foundations of quantum mechanics with the people that I think string theory is a little bit out there, but like if let's say you're trying to tackle quantum gravity or some important topic or.
So you're saying get people to talk about quantum gravity. So then invite people who have specialization at the deepest levels of quantum and the deepest levels of general relativity.
Yeah.
Okay, that's
put them in a room
idea.
together and see what happens.
Right. We should host that conference.
The Eigenbros.
The Eigenbros presents.
It would kind of.
Yeah, it would devolve into a.
Well, in this little video, if you watched in the video, I think who was it? There was one guy who he was just like being like he was a character.
Yeah.
I don't know who it was, but he stuck his tongue out. He was like, It was funny.
Yeah, I'm sure they got down.
Yeah, I mean, look, they debated for a little. There were some people that were just like they essentially could have done a. What is this called?
Hang loose.
Yeah, I mean,
yeah.
I mean, scientists are not. I think we need to have more rock star type things like this.
Even a version of that with like maybe not the mega minds, but if you had like Sean Carroll and Brian Greene and
right.
And maybe
imagine
even
making it an
Michio
event,
Kaku and
right?
Neil deGrasse Tyson. That'd be a cool ass event to see. I think they've done that, but the format still wasn't as cool. It was kind of like a stage presentation for the audience.
Yeah.
That would still be an interesting thing to watch.
It would be interesting to watch, but I think I would love to have it where it's like you have a lot of debate.
Mm-hmm.
You have a lot.
I would love to see one with Ed Witten and like Cian Yang, and like who else? And like maybe Leonard Susskind. I don't know what his field is.
Yeah. He's quantum gravity.
Okay.
Yeah.
Malda Sena, Nima Arkani Ahmed. Yeah, I think that'd be
just
pretty
a lot
cool.
of interesting.
Or maybe
minds.
even like throw in guys like Peter Shore.
Yeah, some really famous experimentalists.
Yeah, Lord, he's a computer science physicist guy.
Yeah.
He made the Shor's algorithm, right? Maybe like Grover, people who just have really good knowledge on like how quantum systems work.
You know what I'm saying? Like,
Yeah, that'd be kind of cool.
Yeah, just to see what comes out.
I guess it's Twitter.
No, I don't think there's. I don't think that's like.
That's not really.
I think it's different when you have. Yeah, I think it's different when you have people like in a
room.
You're almost forcing them to debate and talk about something. It's like you gotta like hash it out.
But what would be the topic then? What do you think would be some good topics to discuss?
Let's say you were talking about
how to approach quantum gravity.
Yeah, maybe like methods in approaching, maybe like quantum foundations.
I feel like the guys like Peter Shore and Grover would be left out though because they don't know.
Well, I mean, it would be interesting to see how they would tackle it.
Yeah, probably from some kind of weird computer science, Wolfram or something.
Yeah, I mean, but these are kind of the things that you, if it's a left angle, if it's like an angle that hasn't been, you know what I mean? Like you need to have these people, left field kind of thing, just to kind of, you know, we need to have more outside the box kind of thinking.
Yeah, it'd be a cool idea. Yeah. I don't know how productive it would be because I think these problems today are just so deep now. Yeah. I don't know how they could do it, but maybe there's inspiration that could be gained, for sure.
But to me, the philosophy that Solvay had was like, I'm a lover of science. I love the discovery that's going on and the topics that are centered around this. I'm going to bring the world's best minds.
I see. And regardless, the world's best minds will come up with some interesting questions and debate topics and whatever.
Yeah.
Yeah, I think it's a cool idea.
We need to have that exploration mentality back. This is what I'm
Maybe we can organize it for real.
Dude, that would be awesome. I mean, imagine if we were like, hey,
let's need more clout though.
I don't even think you need that. I think you could sort of position yourself as like, we're trying not to make the Fire Fest of science, but but we want to like.
Right. I guess if we really wanted to, because all you'd have to do is just find a space that everybody, in a space and a time, right?
Right.
That's it. And if you can somehow organize
a conference.
Yeah, organize a conference in advance enough, because these people are real busy.
Yeah.
And they had trust enough in you that they're like, okay, this could be interesting. And you had some people to confirm that they would be there. Like if Ed Witten was there, you would automatically just sell that as like Ed Witten's coming.
What's their asking price? It's and a lot of it, I think you could do it through crowdfunding too. Imagine if you convinced enough people like.
Oh, well, I wouldn't want to even do it for a price. They'd have to do it for the love of science.
Oh, really?
Yeah, because that would just be so hard.
Well, I would try to crowdfund it.
So you would want to pay them to come. I think that kind of cheapened the event a little bit. Because now they can just be there for the check.
Okay, how about this? How about this? You say, room and board paid.
That could be reasonable.
Like everything like the living expenses while you're there.
That could be reasonable.
Paid.
Yeah. Because I feel like scientists, they would just do it for the love of the game anyway. But the room and board paid would definitely be a massive
but that's what I'm saying. Sure. Like if you could crowdfund something like this so that you can get these great minds in the same room to talk about topics that are like we need that. I think we need that.
I think it's a cool idea.
Yeah. Hey, if y'all like the idea, please let us know. Like for me, I'd be down to to just start a GoFundMe and just put it out there and just be like, let's see if people are interested.
Right, and just have the list of people we want, the all-star list.
Yeah.
That'd be cool.
Or maybe have some ideas, maybe first crowdsourced big conference like this.
Solvay 2020.
Yeah.
2022.
I'd be down.
It's giving me Coney 2012 vibes.
But let's bring back this exploration aspect of bringing great minds together.
Indeed. I think that's our time. Let's I guess for the comments, guys, who would you want at the 2022 Solvay? Or let's just say future Solvay, because I think 2022 is a little bit too ambitious.
Yeah.
let's say the Solvay of the new millennium.
The Eigenbros presents
Solvay Conference.
Yeah. Yeah. So what do you think? Leave it on the comments below and make sure to like and share and subscribe if you haven't already.
And then, guys, check out Eigenbros.com, Eigenbros on Instagram, Eigenbros on Twitter, Eigenbros2 on TikTok. And then patrons, guys, thank you once again. Guys, if you want to be in our Patreon, it's patreon.com/Eigenbros. We just ask for $1. You get access to 30-minute podcasts every week and also the Discord. I think it's a pretty good deal.
I think that's it. Yeah, it's pretty good. And I think that's it.
That's it.
All right. See you later.
Later, guys.